Will here from Polyhedral Playground. As you may be aware, I've been kind of on a LiveMath kick lately. They're bringing it back to life, getting it going on modern machines here, and it has just been a huge part of the math art and stuff that I've done for my classes. And I don't know, I just like it so much. And today, rather than an explainer video, I think I'm going to be looking just sort of an analysis of two different things that kind of do the same thing and why I might want to use one format rather than the other. And this is multi-curve plots or grid plots. So in this first column here on the left, these are all what I would call a multi-curve plot, whereas on the right, these are grid plots. So let me just show you the difference here. When I open up the details, these 6 blue lines, blue curves here, are being created by this statement right here. This is a curve at x comma y, where x goes from left to right, and c goes from 0 to 3. This is a thing that LiveMath allows you to do, even though it's essentially a one-dimensional curve. They give you the option of just, it's kind of like multiplying by the second variable, and it treats it like an index, right? So the thing is, it's sampling a bunch of values of c between 0 and 3, and it's plotting those points. And so notice what I have is the cosine x plus c. So different values of c are shifting that cosine curve a different amount. So the one down on the bottom here, the cosine curve hasn't been shifted at all. This one here has been shifted up, whatever it is, right? And this one's been shifted up. And you can see that it doesn't actually get to 3, because if this was shifted up to 3, this should have made it all the way up to 4. So it's doing several equally spaced, but it doesn't actually get to that last endpoint of 3. Interestingly, I can use the grid density to add more curves, right? And I decrease the grid density to eliminate the curves. And at the lowest density, it doesn't plot anything. So you bump it up 1, so you're at grid density 2, and it's plotting 6 curves. And it's choosing the range from 0 to 3, divided into 6. So it takes the first one, 1/6 of the way, 2/6 of the way, 3/6 of the way, 4/6 of the way, and 5/6 of the way. One thing to notice too is that at the lowest resolution, the density of the plot doesn't seem to go down, in that it's nice and smooth. It doesn't get jagged. Now, the alternate way of doing this is right here with a grid plot. Now, every single one of these graphs in LiveMath comes with a grid in it, and it's all hidden in the graph building blocks. You can see that there's grid lines for the horizontal lines, grid lines for the vertical lines. I may have those backwards. There's 2 axes in there, and there's a bunch of definitions. That's all just comes hidden with the plot. But you can use those grid plots as essentially an indexed curve plotter, because what it's doing here, just take a look. This is grid lines at x comma y, where x equals left to right. That's a lot like this. And then for each value of c between 0 and 3, and there's this separated by, and you get to choose them there, and you get to choose the color and the style. You could choose the color and the style over here as well. So these are grid lines. And I can get a very similar thing. Notice from 0 to 6 separated by 0.5 is similar to what this one was doing, because this was at 0, a half, 1, 1.5, 2, and 2.5. So I've got those things plotted here, but this actually does all the way up to the end. It does the last one. One thing I do notice here is that because these are grid lines, that the built into the LiveMath grid thing is that it emphasizes 0, it's going to emphasize 5, it's going to emphasize 10. So you can see some of these lines, you look at the grid in the background, some of them are darker than others. So there's a bit of fading out for the non-prominent ones. Now, that's on normal. If I bump it up to, like over here, these were on heavy. If I bump that up to heavy, then there's no difference between the first one and all the others. Thing to notice here is that the grid density doesn't change the number of curves. The grid density actually changes how smoothly it's drawn. You got to bump the density up to see some smoother curves. So to change the number of curves, you're just changing the step size. If I want to double the number of curves, I could say, well, rather than stepping by 0.5, I could step by 0.25. Or I could step by 1, right? I could change this to anything I want, and you've got that. You've got that ability. So I like this. I like these grid plots for that reason, that I have way more control as to what's being drawn than I do over here. I mean, this is kind of cool to have this, but I like it. I like it better over here. One thing that's interesting here, this plot right here is the same function. This is still referring to that cos x plus c. It's here, but this time all I did was I swapped the order of, rather than saying x equals left to right and then c equals 0 to 3, I said c equals 0 to 3 and x goes left to right. And what you have at this point is that it's sampling different values of x and taking all the values of c between 0 and 3. And so, you know, as I decrease the density, you're seeing fewer values of x. And so if you look at just the bottom, that would be the cosine curve. Actually, 0 is over here. Let me slide this over some. Well, matching that one. I have 0 pushed over here. But that would be the curve with c equals 0. And up here would be the curve with c equals 3. And all the ones in between are that cosine curve for different values of c. But here, it's connecting them based on different values of x. So for each value of x, it runs through all the different values of c and makes those connections. And I get more lines by increasing the grid density and fewer lines by decreasing the grid density. On the other hand, over here, right, this is the same kind of thing. Why does it? Let's redraw that graph. There we go. This time I'm using a grid plot. And again, this is instead of where x equals, now I have where c equals 0 to 3 for each value of x between left and right. And now I'm choosing the density by saying how far are these x values being separated by. Right? I can separate them by 1. I can separate them by pi. Interesting. Interesting. I can't, as I'm recording the video, Alt P is how I would typically get the letter pi, but Alt P is turning the recording on and off. That's kind of funny. So let me get pi another way here. Whoops, that's not what I wanted. Let's grab pi out of that and then say divided by 2. So I can do gaps of pi over 2. I can do whatever I want here, right? 0.1. So you can essentially fill a region in that way. Lots of control when you're using the grid plot. Less control when you're doing the multiple curve plot here. Okay. I can also do this with parametric, right? So this is a curve where c now is being used as the radius of the circle. So t is going from 0 to 2 pi. Cos t sine t is going to draw me a circle in that, and the c is going to be the radius. So the radius is going from 1 up to 4. Of course, it doesn't get 4. It doesn't, in this way of doing it, never plots that last one. Where here, when I use a grid line, I can do, you know, where t goes from 0 to 2 pi for each value of c between 1 and 4 separated by, and I can pick my, you know, how often am I going. This goes all the way up to well, this doesn't go up to 4 because I'm jumping by pi over 6. So let's jump by, what's this doing? This must be going by a half. So let's go by 0.5 there. And that should make it all the way out to 4. Right? So there's 1, 1.5, 2, 2.5, 3, 3.5, 4. I've got all those. Right? Yeah, so curve plots, which are actually parametric plots, they're indexed parametric plots by either using this extra variable here or using a grid plot in order to do it. A little more control when you're using the grid plot than when you're doing it that way. And again, the density over here is increasing the number of curves you're plotting, where the density over here is really increasing or decreasing how accurately the graph is being plotted, right? All of the graphs. This is just the same thing as the one above with the variables turned around. I don't need to say too much of that. I like this with animation. Just so what I've done here is I've animated it, and so in a sense now I've got three variables I'm working with because the curve plot has my t and c, and t and c are drawing circles of radius c. Yeah, so the c cos t and the c sine t, and then I'm also using the c to pick a direction that the circle's going to travel in when a, my animation parameter, is allowed to change. So I've got t, c, and a, and what I can do is I can do this. So the circles start off concentric, but then each of the circles moves off in its own direction depending on which circle it is, and it just kind of looks pretty trippy, right? Now that's done with the multi-curve plot. This one over here is done with a grid plot. Same formula. Although this is an interesting thing because the curve plot, for whatever reason, this multi-curve plot doesn't know how to figure out what's here if it's not just a vector. Notice I have here is I have one vector plus another vector. The result is a 2D vector, and the grid plot can figure it out. If I tried to add something on, if I tried to take this and shift it, and this is quite often the way I would shift things, shift a graph, is I have the graph sent one place, and I just want to move it over. I would just say plus 1 comma 0 to move it over, but as soon as I do that, it doesn't know what to do. So the curve at, when using without this extra variable in there, it would handle that plus 0.0, plus 1 comma 0, no problem. But with the extra variable in there, it doesn't handle it. So let's get rid of that. So that one will still plot, and there we go. But over here, it does, that this grid plot is able to handle the multiple vectors as long as they resolve to be a vector, then that's good. If you think about how polar plots are done, that you actually quite often will use the function from polar or to polar, and that would be put on the outside of this, and this curve plot wouldn't be able to handle it if you have that extra thing there. The grid plot does. It's still, the animation looks the same, but the number of circles is controlled here on the inside. That is, I'd have to change my step size. If I want fewer circles, take a bigger step size. If I want more circles, take a smaller step size, where here, fewer circles is achieved by decreasing the grid accuracy, and more circles is by increasing it. And again, this is just the same thing with the variables turned around. I think it's a fascinating animation. You can see the big circle there going around the outside, and the littlest circle is just the dot right there. The other circles get lost in just the curves for constant values of c. So no constant values of t. Sorry, what is that? C is in front, so yeah, these are constant values of t. So each value of t is showing you all the points on the different circles for that value of t, and then you pick the next value of t and all the points on the different circles for different radii. Interesting stuff there. So because we have this ability to like add vectors together in the grid plot where you don't with the multi-curve plot, it made me think I could do something really silly here. And this graph with four different curves plotted is a single grid plot. And the way I did that is I said grid lines at, and I've got this piecewise function where it's saying, t is going from 0 to 1 for each value of y between 1 and 4. So y is, I'm using like I've been using for c before. It's just going to count by 1. I'm separated by 1. And so if y is equal to 1, it's going to print, it's going to do this curve. When y is equal to 2, it's going to do that curve. And 3, that curve. And then if none of those happened, 1 is definitely bigger than 0, so it'll definitely do this one. And yeah, and I've got 4 separate curves plotted, all with a single grid plot. Okay. That's kind of silly because I could just do 4 separate plots to do that. But at the same time, it got me thinking that I could do something like this. So here's with animation. I have one grid plot that's plotting F. Where is F? F is defined up above here. So F is a figure 8. So it goes back and forth in the x direction 1 time for every 2 times it goes up and down in the y direction. So there's a figure 8 here that I am putting a circle, this one right here. So it's S goes from 0 to 2 pi. This is drawing a circle, and then I'm shifting it by some value on that lemniscate. And it's being shifted differently depending on what C is. So I currently right now I'm saying I want 3 circles, and each of those circles, and this is animated, t equals 0 to 2 pi, and so as t increases, it's moving around that circle. But because each one of the curves, each one of the circles is shifted differently along the path, what you see is it looks kind of like it's juggling. And I set this up all as functions of n, right? That this is c goes from 0 to n minus 1, and this is 2 pi divided by n. I can change the number of things. I can say, give me 4 of them. And there's 4 things that'll go around, and they kind of cross each other. It actually works a little better here if I choose odd numbers so that they really look more like they're juggling. Except it's kind of a funny thing in that if you're juggling with heights, the heights would be different if you're juggling 5 balls than if you're juggling 3. And this just keeps it all the same. I'm just following that one curve. So here's 7, and here's 7 circles. Again, this is all one grid plot that is creating this set of 7 circles all animating around this thing. And the more this goes, it almost feels like sort of like moons orbiting in a figure 8 around two masses, one right here and one right there. And the higher the number gets here, the more dense it gets. Yeah. Crazy car race, the figure 8 car race that they used to have in those. Maybe they still do, some of those car places that do racing, track racing. So when I got thinking of this, it's like, oh, I could actually make, because I made a juggler years ago with LiveMath. It's like, oh, I could do a better juggler function here. So I could do a single, I have n equals 7. Let's go down to n equals 3. Oh, there's another issue here that I'm going to discuss. But let me hide it for a moment. Let me take this surface and get rid of it. And get this surface out of there too. So here's a similar thing, except that you can see sort of a jerkiness in this, and that there's 2 different functions. I'm trying to make this look more like real juggling. So while it's in the air, these things are following along a parabola. And then when it's essentially been caught and being brought back in to where it's going to be thrown again, that's an arc of a circle. That's half a circle down there. So the hand essentially is following a circle, and the ball is following a parabola in the air. And again, I have it set up in function of n, so I can say, okay, give me 5. Give me 5. There we go. And it's juggling 5. Now I can show you the function that's doing this. It is a piecewise function in that there's 4 pieces to it. Where's the path of the ball's function? So this is saying, to begin with, I'm thinking of the first ball as being released at the origin and flying off to the right, and it will be following a parabola. This is linear in t in the x direction, and it's an upside down parabola in the y direction that will land just the right number of time units later. It'll then travel, so it takes n minus 1 units of time in the air, then it takes 1 unit of time to be in the hand moving along a half of a circle, and then it's going to be thrown in the other direction. So again, this is now the linear x coordinate and quadratic y coordinate with the t shifted down because we've advanced we've advanced time to be throwing now halfway through the cycle. And then for the last time unit, again, has been caught with the other hand and being brought and thrown in. So that's the path of the balls, depending on various things. And the balls are circles that move along the ball path. This modulus is saying we're going to essentially just let time be between 0 and 2n, and we're shifting by 2c in that direction. So anyway, it'll do 5 balls. That starts to really look more like what juggling is. Down at the bottom here, these nice circular arcs of what the hands are doing. And the balls are moving in parabolas. It's just they go up, they kind of slow down at the top and come back down again, speeding up. So it's right now it feels like very slow gravity, like maybe juggling on the moon or something. But yeah, that's what it is. Let's bump this up to 7. I like 7 balls here. Let's do 7. And notice the time is going from 0 to 2n. So as I bump up the number of balls, the length of time is increasing as well, twice that. Right, so this is 14 beats. So each ball, 1, 2, 3, 4. Right, those are the beats. That's 1 unit of time. And technically, the way I have it done is that if you watch, as each ball is launched, there's another one that's landing in the other hand. Right? So the last thing I want to say about this, I'm using grid plots here. The curve plots, just the multiple curve plot wouldn't allow me to be able to do this, but the grid plot does. It's a really nice indexed curve plotter. I got thinking about other things too, and I wanted to say, I want to change the color of the background, which LiveMath doesn't really have the ability to do. I thought, oh, I can just plot a region in a color that I want and just put it behind everything. I mean, the way LiveMath works is it looks all these things. It's plotting the first thing on the list first, and then the second thing, and then the third thing. So as they overlap, you would see them. You would see the one printed last on top, and it occurred to me that all these grids that are always there, they always start off up at the top of the thing, so they're printed first. And I was just thinking I could just throw a region behind it and have the grids printed on top of it. But apparently the grids are always sampled first. So what I'm going to do here is I've got the hands in here. So I have this so that each hand is a circle. I'll just have one hand for the moment. Watch what happens as I go. It comes over, catches the ball over there on the right, holds it, and then throws it. The surface, that purple surface, is being plotted supposedly before the grid plot because it's first in the list. But yet you don't see the ball when it's in the hand. The grid plot is put first. So this is a little disappointing that that's going that way, but still I think it's pretty interesting. Let me get both hands going on this. Let's get rid of that one. And so you can see both hands catching the balls over on the left, or sorry, on the outside, and throwing them on the right side. This would be your standard cascade. Any jugglers out there know the names of the juggling patterns. So there's a 7-ball cascade, and the hands are just moving in beautiful circles, catching the balls on the outside, throwing them on the inside. This is why I do math. This is why I love LiveMath. I can just do formulas and end up with really cool animations and pretty pictures and whatnot. And I'm always trying to figure out, how do I do something different? How do I do it better? How can I get that ball to actually be shown on top of the hand and not be hidden behind it? Things like that. How do I do that? So anyway, there's a bit of an analysis of multi-curve plots versus grid plots, and I really, really like the grid plot as this, what I would call an indexed curve plotter. So there you go. I've been Will with Polyhedra Playground. Keep having fun doing your math.